Hello everyone, myself Jansi from Department of Computer Science and Engineering, USN 1VE20CS055 from the semester 6 and section Aryabhatta. Now we are discussing about the topic generate the object code using SIC/XC source program related to the subject system software and compilers.
See here for SIC, okay, for the architecture SIC. So let's try to understand the given question. A set of assembly language code is given to you and for all these mnemonic operations its opcode value is also given, right? Over here opcode value is also given. So what this program does is, let us look at the declarations first. So there is a output variable where you are declaring this output variable, right, and then initializing it with a byte value 05, it's a single byte value. This is an assembler directive. Similarly, word is also an assembler directive where at the address location labeled 0 you are storing, initializing and declaring and initializing the value 0 in this location 0, and the reserve byte is used to reserve some specified amount of bytes starting from the location buffer and length. So buffer 400 bytes are being reserved starting from the location labeled at buffer, and 2 bytes is being reserved starting from the location labeled at length. Then this is our program. So in the program start 105D means the program is being loaded from the address 105D. So the first instruction LDX0, so loading the index register with the value contained in the location 0. 0 contains 0. So loading accumulator with loading the index register with the value 0. Then loading the register T with the value contained in length. Length contains 2. So the register T contains the value now 2. Now TD. TD is for testing the device. So which device you are testing? Output. Output contains the output device specified by the value 05. So whichever is the output device, you are testing the device before you can read or write something from the device. So if the device is busy or if the device is free, based on that the status code will be set. So if the device is busy, in that case the status code will be set as equal to. If the device is free, the status code will be set as less than. This we have already seen in our previous lectures. So until the status code is equal. Equal means the device is busy. So jump on equal to. If it is equal, you again jump back to this location and keep on test the device until the device becomes free. So when the status code is not set as equal, this condition will not be met. It will come to the next instruction. So the next instruction is LDCH. So loading the last byte in the accumulator or the character. Character takes 1 byte, right? So loading the least significant byte with a character. So from where are you reading the character from? From the address buffer. This is indexed mode of addressing. So buffer contains some value. So the buffer points to this address. So buffer comma x means whatever is the base address of buffer comma x. So this is like accessing the 0th location of an array since x contains the value 0. So buffer of 0, whatever character is there in buffer of 0, from there the character is being read and stored into accumulator, and it is written to WD is write to device. It written to the device output, whichever is the device that points to the number 505. Then it uses the instruction TIX to increment the index register by 1. So it increments the index register by 1. Now index register contains the value 1, and that value is being compared with the value contained at the location length. Length contains 2. So 1 is being compared with 2. Now again the status code will be set. So since 1 is less than 2, jump on less than condition will be true, and you again come back to this location loop. So this runs for one more iteration where the index value will be incremented by 2, and when it's compared with length, this condition will not be met, and it is R sub, return to subroutine wherever it was called. And then finally all these are the declarations, and the assembly language ends with the end instruction. So end instruction contains a first executable assembly language code which starts from WREC. So this is an overall understanding for the program. Now the first step is to fill out the location values. Okay, you are required to fill out the location values. So here it says that it starts from the address 105D, right? So it starts from the address 105D. Now you have to take that means the first instruction. So this is the first instruction. It starts from the location 105D. Now the address will be added with the length of each instruction to calculate the next address. Unless and until you come across an assembler directive, the length of an instruction, okay, we have only a single format in SIC. So the length of an instruction in SIC is here we have 3 bytes. So 15, 16 plus 8, 24. 24 bits, 3 bytes. So the length of an instruction is going to be 3 bytes. So what you have to do, the length of each of this you can write down. So this is 3, 3, 3, right? This instruction is also 3, 3, 3, the length of the instruction. So let's write till here, and we'll try to work out the assembler directives after filling out these values. So you have to keep on add the value 3 to the address starting from the location 105D. So use your calculator for that. So calculator helps you in doing the hexadecimal addition. So all these values are given in hexadecimal. So you can use a mode base 3. So it's hexadecimal value. So 105D, right? 105D, where do we have? Yeah, 105D plus 3. If you add, you will get the location 1060. So that is the next address, 1060. So this is the address of the instruction LDT. Now if you again add 1060 with the length of the instruction, you will get 1063. So you can keep on add with 3 till you get all the address locations. So I have filled out all the values till this instruction are set. The address is 1075. Now let us look at the next statement, which is an assembler directive. So it says reserve, like you have a value, right? You are declaring a value byte 05 to the location output. So that means it's a single byte, right? So so after this instruction, which is also 3 bytes, the next instruction is 1078. So since you are reserving only a single byte for the output variable output, okay, for this variable output, you are reserving only a single byte where you are loading it with the value 05. So at the address 1078, the value 05 will be loaded. So the address of the next instruction will be 1079. So please remember that the assembler directives are pseudo instructions. It is not getting converted to object code, and it is not getting stored, the instruction as such is not getting stored. The declaration, whatever variable you are declaring, that variable gets stored in the location. So again, this next instruction, for this instruction, it's a word, right? Word is 3 bytes. So you will get this instruction. If you add 1079 with 3, you will get 107C. So you can verify that 1079, if you add it with 3, you will get 107C, right? 107C. So 107C. Now again, from this location, here, what is the length? How much bytes are going to be reserved starting from the location buffer? So 400 bytes are going to be reserved. So remember that this is a decimal value. So you have to add the equivalent hexadecimal value to this address so that you can reserve that many number of bytes. So if you convert 400 decimal value to hexadecimal, okay. So now I want to convert, let's try to convert the decimal value 400, okay. So 400 is a decimal value. So its equivalent hexadecimal is 190. So if you add 107C with 190, now again 190 plus 107C, right? 107C. If you add it, you will get the location as 120C. So this instruction will be loaded at the address 120C. Not instruction, whatever has to be reserved for the next instruction. So 190 bytes is being reserved for the buffer, for the variable buffer. Next, 2 bytes are going to be reserved for the address length, 2 bytes. So whatever instruction comes next, it will be loaded from the instruction 102E, since you are reserving 2 bytes. So this is your first step. You will write down all the addresses, and with these addresses, next step is we will be computing the object code. So now our next step is each of these instructions has to be converted to its equivalent object code. So how to convert? It is with the help of the instruction format. In SIC, as we have told before, there is only one instruction format where the first 8 bits, in the first 8 bits, the opcode value will be stored. Then the next 1 bit determines whether the addressing mode. SIC supports 2 types of addressing mode, direct addressing mode and indexed addressing mode. So only if you have an indexed addressing mode coming in an instruction. Say for this example, if you take this example, it takes indexed addressing mode because you have the index register coming in the instruction. All other instructions come under direct addressing mode. So only for indexed addressing mode, this bit will be set to 1. And the remaining 15 bits, you will have the address stored. So now our step is, you have to take each of these instructions and in order to convert it into the object code, you have to fill the suitable values in this format. So let us look at the instructions one by one. Okay, so the first instruction LDX. So LDX 0 is the first instruction. So the opcode value, right? What is the opcode value? It will be given to you. LDX, the opcode value 04 and the target address. What is the target address? Is the address that points to the location 0. So the 0 location points to 1079. So the target address is 1079. So all you need to do is fill in this box with these values. So the opcode is 04, right? So 0 in hexa. Each of these is a hexadecimal value. So you have to write it in binary. So 0 in binary and 4 in binary would be 0100, right? Then it's not indexed addressing mode, so you will have a 0 here. Then you have to write 1079 in the remaining 15 bits. So each of this takes 4 bits each, right? So 1 means it is 0001, then followed by 0. This would be 0. Then 7 is 0111 and 9 is 1001. So you have to see that it's actually 16 bits, but only 15 bits are used to store this field. So the most significant bit will not be stored in the address. The 0 will not be stored in the address field. So this is the equivalent binary value equivalent to the instruction LDX 0. This is how you convert the assembly language instruction to binary. Now what is the equivalent hexadecimal? You represent this in hexadecimal in order to fill this table. In order to fill this table, you have to write its equivalent hexadecimal. So you group the numbers in terms of 4 bits, right? So in order to write the equivalent hexadecimal, it will come this way. So the first group is 0. The next group you have 4. Then we have 1, 0, 7 and 9. So the object code corresponding to the statement LDX 0 is 041079. So similarly, let us try to do the next instruction. So the next instruction is LDT length. So what is the opcode value is given as 74. So the opcode value is 74 and the target address is length. So length points to the address, the target address points to the value 10120C. All you need to do is just fill the value in this table, in this box. So opcode is 7, right? So 7 is 0111 and 4 is 0100. Now this is not indexed, so you will fill the value 0 here. Now equivalent to 120C, just fill in the binary value. So 1 is 0001, 2 would be this, then again you have a 0 followed by C. So C is 1100. So remember this, strike off this most significant bit and then write its equivalent hexadecimal value. Group it in terms of 4 and write the equivalent value. So again you will get the value as 74120C, right? So this is the value equivalent to the instruction LDT length 74120C. Okay, now let us look at the next one more instruction, TD output. So TD output, the mnemonic code given for TD is the opcode given as E0, right? So the opcode value is E0. The opcode value is E0. And what is the target address? The target address is given at 1078. Output points to 1078, right? So now all you need to do is convert this into binary. So E is 1110 followed by 0. Now again it's not indexed addressing mode, so this would be a 0. then fill in the remaining target address in this address field. So the target address is 1, followed by 0, followed by 7, followed by 8. Now again strike off the most significant bit, group it in terms of 4 bits and write the equivalent hexadecimal value. So the equivalent hexadecimal value you will get it as, okay, I'm just writing this equivalent hexadecimal value. You will get it as again E, okay, E0 1 0 7 8, E01078. Now just similar to that, you have to fill in the other values, okay, other values also. So for JEQ, if you follow the same steps, you will get the value as for JEQ you will get 301063. You can once verify. Now I'm going to show you how this LDCH will work. So the difference is, here you have X index register coming. So the value that will be loaded to the X field will be a 1. The remaining steps are the same. So LDCH, the opcode value is 50. Okay, so the opcode value is 50, and the target address is the address that points to buffer. Buffer points to 107C, right? 107C. So your opcode 50. So this is 5 and followed by 0. Then again 0001 followed by this 0. Then 7 you have 7, and then followed by C value is 1100. Now you will strike off the most significant bit. What is the equivalent hexadecimal value that you will get when you group? So now you will get the value as again you will get 5 0. So 1001, which is a 9, followed by 0 7 and C. So this is the value that corresponds to LDCH buffer comma X, which is 50907C. So similarly you can fill in all the values for these 3 instructions also. So for these 3 instructions you will get the value for WD, you will get the value as DC 1078. You can once verify. For TIX you will get the value as 2C120C, and for J jump on less than you will get 3810 and 63. Now I'll show you how to write for RSEP. So for RSEP, the opcode value, what is the value for RSEP? 4C. So the opcode value is 4C, right? 4C. Now there is no operand mentioned in the address field. So here the address, target address will be a 0. It's all zeros. So you have 4. 4 is 0100. C is 1100. Now it's not indexed. So you will have the target address as full zeros. Okay. This is how you will convert RSEP. So now when you write the equivalent hexadecimal value, you will get 4C followed by all zeros. So this will be your object code corresponding to RSEP. 4C followed by zeros. Now assembler directives. Okay. So please do recollect that assembler directives are not converted into object code because they are not stored in a memory. Only the values and the bytes are being reserved depending upon the assembler directive. So here byte 05. So the value 05 is directly stored in this address 1078, and the value 0 is being stored in the address 1079. Then 400 bytes are being stored for this location. 2 bytes are being stored in this location. So this is the object code generation for the corresponding set of instructions that is given. So I hope this as hand assembly. Okay, so this is your hand assembly of SIC program, where given a set of programming statements in assembly language, first you have to determine the addresses. So make use of your calculator and calculate the addresses depending upon the length of the instruction. Now the next step is, in SIC, this is an easy process because you only have one instruction format. So all you need to do is just fill in the values. Opcode value will be given to you, and you just have to fill in the box with respect to the values given in the opcode, and you have to calculate the target address. So your symbol table, so this is the opcode table. So how will your symbol table look like? Symbol table will contain all these labels, okay, all these labels and its equivalent addresses. So your, for example, if you want to see, here the opcode table is this. Now your symbol table, okay, your sim tab. Your symbol table will contain the labels WR, REC, then you have W loop, then you have output, 0, buffer, and length. So we have seen that assembler takes 2 passes in order to convert the assembly language to object code. So in the first pass, all the addresses will be labeled, and the labels will be assigned with these addresses. So WRREC will point to the address 105D, W loop will point to the address 1063, output 1078, 0, 1079, buffer 107C, and length 120C. So this is your symbol table, okay, and this is your opcode table. So I hope this video was informative to you. Thank you so much for watching.